Electric fields are a fundamental concept in physics that play a crucial role in the behavior of charged particles and the operation of many modern technologies. An electric field is a region of space surrounding an electrically charged object, in which other charged objects will experience a force. The strength and direction of the electric field depend on the magnitude and distribution of the charge producing it. The study of electric fields began with the pioneering work of Michael Faraday and James Clerk Maxwell in the 19th century, who developed the fundamental laws governing electricity and magnetism. Maxwell's equations, which describe the behavior of electric and magnetic fields, revolutionized our understanding of the physical world and laid the groundwork for many technological advances, including radio communication, electric power generation and transmission, and modern electronics. Electric fields are present in many everyday objects and phenomena, from the electrical charges in our bodies to the static cling of clothes fresh out of the dryer. They are also key to the operation of devices such as electric motors, generators, and transformers, and are used in a wide range of applications, from medical imaging to space exploration. Understanding the behavior of electric fields is essential for many fields of science and engineering, including electrical engineering, physics, chemistry, and materials science. By studying electric fields, researchers can gain insights into the properties of materials, develop new technologies, and solve practical problems related to energy production, communication, and transportation. In this context, this field continues to evolve as new technologies are developed and new applications are discovered, making it an exciting and rapidly advancing area of research. Electric fields are generated by the presence of electric charges, either stationary or in motion. The generation of electric fields can occur in a variety of ways, depending on the nature of the charges and the materials in which they are located. Some of the most common methods for generating electric fields include electrification by friction. When two objects are rubbed together, electrons can be transferred from one material to the other, resulting in a net charge imbalance and the creation of an electric field. This phenomenon, known as electrification by friction or triboelectricity, is the basis for technologies such as electrostatic generators and photocopiers. Electrochemical reactions. Chemical reactions can also result in the creation of electric fields. For example, batteries generate an electric field by converting chemical energy into electrical energy through an electrochemical reaction. Electromagnetic induction. When a magnetic field changes with time, it can induce an electric field in nearby conductors. This phenomenon, known as electromagnetic induction, is the basis for electric generators and transformers used in power plants and electrical grids. Electrostatic induction. Electric fields can also be induced by the presence of nearby charged objects. When a charged object is brought close to an uncharged object, the electric field of the charged object can induce an opposite charge on the surface of the uncharged object, resulting in the creation of an electric field. Moving charges. The motion of charged particles can also generate electric fields. For example, the motion of electrons through a wire creates an electric field that drives the flow of current. Piezoelectric effect. Some materials, such as quartz and certain ceramics, generate an electric field when they are mechanically deformed or subjected to pressure. This phenomenon, known as the piezoelectric effect, is the basis for technologies such as sensors and actuators. The generation of electric fields is a fundamental aspect of the study of electromagnetism and is essential for understanding the behavior of electric charges and the development of technologies that rely on electric fields. Electric fields have several characteristics that help define their behavior and influence the behavior of charged particles within them. Some of the key characteristics of electric fields are as follows. Electric fields are vector fields. Electric fields are vector fields, meaning that they have both magnitude and direction. The strength of the electric field at a particular point is given by the electric field intensity, which is a vector quantity. The direction of the electric field at any point in space is given by the direction of the force that would be exerted on a positive test charge placed at that point. Electric fields are created by charged particles. Electric fields are created by the presence of charged particles, such as electrons and protons. Any charged particle, whether stationary or in motion, generates an electric field in the space surrounding it. The strength and direction of the electric field depend on the magnitude and distribution of the charge producing it. Electric fields can be uniform or non-uniform. Electric fields can be either uniform or non-uniform. A uniform electric field has a constant strength and direction throughout the region of space it occupies. A non-uniform electric field, on the other hand, has a variable strength and/or direction in different parts of the space it occupies. Electric fields can be static or dynamic. Electric fields can be either static or dynamic. A static electric field does not change with time, while a dynamic electric field varies with time. Dynamic electric fields can be produced by oscillating charges or by electromagnetic radiation. Electric fields can exert forces on charged particles. Electric fields exert a force on any charged particle placed within them. The direction of the force is determined by the charge of the particle and the direction of the electric field at the particle's location. The magnitude of the force is given by Coulomb's law, which states that the force is proportional to the product of the charges and inversely proportional to the square of the distance between them. Electric fields can do work on charged particles. Electric fields can do work on charged particles, causing them to gain or lose energy. The work done by an electric field on a charged particle is given by the product of the force on the particle and the distance it moves in the direction of the force. Electric fields can induce electric currents. Electric fields can induce electric currents in conductors or in the plasma of a gas. This occurs when the electric field causes charged particles to move within the material, creating a net flow of charge. Understanding the characteristics of electric fields is essential for many applications, from designing electrical circuits to understanding the behavior of charged particles and plasmas. By studying these characteristics, researchers can gain insights into the underlying physics of electric fields and develop new technologies that rely on their behavior. Electric fields have a wide range of applications in the real world, from everyday technologies to cutting-edge scientific research. Some of the most significant applications of electric fields include electrical power generation and distribution. Electric fields play a crucial role in the generation, transmission, and distribution of electrical power. Power plants use electric fields to generate electric currents by inducing motion in conductors within the magnetic field. These electric currents are then transported through high-voltage transmission lines to homes and businesses, where they are used to power lights, appliances, and other electronic devices. Electronics and communication. Electric fields are also essential in the design and operation of electronic devices such as computers, cell phones, and radios. In these devices, electric fields are used to manipulate the flow of electrons through semiconductor materials, allowing for the processing and transmission of information. Medical imaging. Electric fields are used in medical imaging technologies such as magnetic resonance imaging, MRI, and electroencephalography, EEG. These technologies use electric fields to measure the electrical activity in the body or to create detailed images of internal structures. Plasma physics. Electric fields play a critical role in the behavior of plasma, a high-energy state of matter that is often used in fusion experiments and other advanced scientific research. Plasma is highly conductive, and electric fields can be used to manipulate and control its behavior, making it a valuable tool for investigating a wide range of physical phenomena. Materials science. Electric fields are used in materials science to manipulate the behavior of materials at the molecular and atomic level. For example, electric fields can be used to create thin films, to manipulate the properties of semiconductors, or to study the behavior of materials under extreme conditions. Electrostatic discharge protection. Electric fields can also be a hazard in some situations, such as in the presence of static electricity. In these cases, technologies such as electrostatic discharge (ESD) protection devices are used to prevent damage to sensitive electronic components and equipment. Environmental monitoring. Electric fields are also used in environmental monitoring applications, such as detecting and measuring air pollution or monitoring the electrical activity of the Earth's atmosphere. In these applications, electric fields can provide valuable insights into the behavior of the natural world and help us better understand the effects of human activities on the environment. Overall, the applications of electric fields are incredibly diverse, and the study of electric fields continues to play a vital role in advancing scientific understanding and developing new technologies that improve our daily lives.